So we'll go through all of the quizzes. I've got all of them loaded in PowerPoint. I know you probably can't read that very well, but I just wanted to make as few slides as possible so I could just be efficient, I guess. So I've got 1 or 2 slides for each of the quizzes. So the exam is just over these first 4 weeks. It's quantum mechanics and symmetry. Okay, point groups of molecules and so on. So let's put the ball in your court. What do you want me to look at?
I guess my first question is, will the kind of questions you see on the test be similar to the questions that we saw in the quizzes?
In my mind, yes. That's always the disconnect. Sometimes I think it's a very similar question, and people are like, where did that come from? But yeah, no, I think it is very similar to the homeworks. There's sort of a maxim in life that people are lazy, right? And professors are people, I know. And so if you've already written all of these questions in the homeworks and you know your students are working against them, it's pretty easy to go in there and grab them and change a few of the words, write them backwards, take the answers and put them into the question, and take the words that were in the question and put them in the answers. So that would be what I call a backwards question, or changing the numbers and things like that. Running a problem backwards. So if I give you it doesn't apply to this, but like in my freshman class, if I give you pressure and ask for change in volume, then on the test I give you volume and ask for change in pressure. So if you can do it forwards, you should be able to do it backwards. On almost all of these types of questions in the homeworks, especially the multiple choice ones, thank you, it's always a good idea to go through all of the answers that aren't correct and their vocabulary words too. So like understand why that's not the answer and what kind of question would be if that were the answer. Do you make sense? So you're just kind of looking at all the options. Now sometimes there's some funny things. I don't think I see it on this particular quiz, but you have the Boltzmann factor and all these different factors, and I've thrown in, like, this was years ago. It was when the O'Reilly factor was a TV show, and so I threw that in as one of the answers. So that's not an actual vocabulary word, but the point is, for those that I've talked about in lecture and so on, be sure that you use all of the non-answers or incorrect answers as a guide, because I'm putting that in there because I think it's important, and you should know all of those too. So that's a good way to study, even if it's multiple choice and you only have one option. Go in and try to use those other options as vocabulary words. Good question. Yes?
For the note card, we can put anything we want, like constants, equations, definitions. Is there anything that you won't allow us to put on the note card?
No, I think that's okay. Yeah. I'm trying to think back to there was one year when I restricted it, but it was because we had a lot of just short answer vocabulary questions on there, and I've switched the testing back to these quiz models. And so, no, I think it's okay. You can put anything you can fit on a 3.5 inch by 5 inch note card. Okay. And so that's the smaller size note card. So be sure you get the right size, or I get to cut off whatever inches I want. But yeah, so, and they need to be handwritten, so that you actually go through the process of building your own note card. It's honestly, when you get to the test, most of the time you very seldom use it, because in making it, you sort of cram it into your head. But it's there as a safety net. I saw multiple hands. Go ahead. Sorry.
Can it be front and back?
Front and back, yes.
That was my question.
Okay, yeah, great. And then you can multiple colors on the pens or highlights and things. I mean, you can organize it. We've had some great. I need to start taking like pictures of them, or we can say share your note card, and you can send them to me, and that way I can get an idea of how creative you are. So that'll be fun. It's just great to see. Yeah, I still have my note cards from when I took PCAP, so they're pretty tiny. They're faded now, but it's kind of cool. Yeah. So you can thank my professor actually for why we get the note cards. Let's see, what was his name? Campion, I think. Anyway. Yeah. It's going to be a short class if y'all don't have questions. Yes.
For homework,
Yes?
Like those last two calculation problems, I just never got them right. I know we were also doing them in the lab that week.
Yes.
And so once I got them wrong on the homework, I didn't realize that I probably did them wrong on the lab. So
Oh.
maybe you can do it.
Yeah, sure. So this one is just, this first one, I believe, the ground state energy in kilojoules per mole for an electron confined to a one-dimensional box of 5.5 angstroms. So this one is going to go straight into that energy equation. So you guys, you just lost your note card, and you've got to recreate this energy equation from memory. Okay? So you take a deep breath, and you say, okay, the energy as a function of quantum number is equal to what's on top? N squared. Okay, so that's good. The quantum number squared. H squared. Let's have a different person give us each piece. And then the denominator? 8. Okay, someone gave me 8. M. L squared. Very good. That's it. You did it. Okay. Piece of cake if we could take the test as a group. Okay, so we'll have... and so this is asking for the ground state. So that right there is a good thing. That's N equals what? For particle in a box. N equals 1. Our options are 0 and 1. But for the particle in the box, the lowest quantum state is 1. Okay. Okay, so N equals 1, so that's 1 squared. And we're going to use all of our units. So Planck's constant, 6.626 times 10. I go to my note card, minus 34 joules, and it's times seconds. Sometimes, rare occasions, people mess that up and put per second. It screws up the units. Okay. In the denominator, we have 8, and the mass of an electron, 9.11, is that right? Times 10. To the minus 31, yeah. Protons 27, so 31 kilograms. Okay. And then L squared. So we have 5.5 angstroms. So 5.5 angstroms squared. Okay. So this will give us our energy in joules. Let's make sure we know how that works, okay? And also, we've got to do something with this angstrom because that's not an SI unit. So most of the time, these questions are about the units. So if you're, I mean, here we had all our constants and everything. We put in all our numbers, but we're going to get a messed up result unless we take care of this angstrom. So we can just do this conversion right here in the denominator. Okay, so 1 angstrom is how many meters? 10 to the minus 10, okay. But we have angstrom squared, okay, so we have to square this whole thing. So we're going to end up with 10 to the minus 20. And I'm going to end up with, let's take one of these joules here, and we're going to end up with joules squared. So we're going to have, one of them is going to be a kilogram meter squared per second squared. And the other one is going to be a joule. Okay. And then we're going to have seconds squared. Do you see how joule times second squared? I get two seconds. I get a second squared right here. So that's there. Okay? Everybody follow that? And I've got a joule squared. 1 joule is here. The other joule is here. See the kilogram meter squared per second squared? That's a joule. I have to do that so that I can kill some of these units, right? Now my kilograms are gone. Okay? And my seconds squared are gone in the denominator and the numerator. And my meter squared on top down here, once I get rid of angstroms, I'm going to have meter squared on bottom. So everything works out to give me joules. I'm just missing the per mole piece. And so I need per mole. So what are we going to end up with here? If I need a per mole, Avogadro's number. Okay. So everything works out. My angstroms squared are gone, and I end up with meter squared down here and meter squared up there. So those are all of my numbers. So here's where we all do our own calculations. So I have 6.626 E 34, change sign, enter. I'm going to square that guy. Let's see. Times. Eight divide 9.11 E 31, change sign, divide 5.5, divide 5.5 again, divide, and 10 to the minus 20 divide 20, change sign, divide, and I get 120 kilojoules. I ended up with 119,000, but they've asked for kilojoules, so that's 119.9 kilojoules, or 120. Did y'all get the same? Okay. So you're doing your calculator right. That's good. This is a lot of powers of 10. Okay. Now, if you really, yeah, anyway, you can hammer through it that way. Yes?
Why isn't it joule squared when you cancel out your units at the top?
What I did was, since this joule times second is squared, okay, so I'll do this. I'll break it into small pieces. So joule times second was squared in there. That's equal to a kilogram meter squared per second squared, which is one of the joules, times another joule times a second squared. So that's what I did, was I broke out one of the joules squared. I just made with the kilograms and so on, so I could cancel all those pieces, and then I left the other joule alone. Is that what your question was about?
Yeah.
Okay. That's what I did up here at the top. I just took that joules squared and broke one of them out. And so then my meters are gone. So all the units worked out, and the numbers worked out. Okay. Now, let's see. I've got this calculation now in this energy in kilojoules per mole, and this is asking for the transition wavelength for the fundamental transition for an electron constrained to a 1D box. Okay, we can look up that calculation, or we can derive it. Like, let's say I didn't put that on my note card. Can't believe it, right? What's the fundamental transition? That's n equals 1 to n equals 2, which is a delta n equal plus 1, right? So let's go ahead and do this transition equation. And so I can put in this E plus delta N minus E of N. So everywhere in our energy equation, there's a quantum number. We put this piece in. So we have in parentheses N plus delta N squared, H squared over 8mL squared minus N squared H squared over 8mL squared. Does everybody see what I've done? I've taken the upper level energy and the lower level energy, and I've taken the difference. That's what the transition is. It's always a difference between energy levels. So I'm calculating here for all possible delta N's. I could put a 1 in there, since we're just talking about the fundamental, and let's just make it a little bit easy. We'll pull all of these constants out front. That's equal to H squared, make sure it's an H, 8mL squared times n plus 1 squared minus n squared. Okay. So what I did in going from here, I just did the delta n is equal to 1. Okay. And so that's going to be n squared plus 2n plus 1. Right, FOIL. So the first, inside, outside, last, minus n squared. Okay, so then the n squareds are gone. And this is going to be my transition equation for that fundamental. When n equals 1, then that's going to be the fundamental transition energy. So that's delta E. So this piece right here, this n equals 1, goes right in for n. Okay. So when I calculate all of that, it's going to be 2 plus 1 or 3 3h squared over 8ml squared. We don't have room to put in all our constants, but that's going to be the transition energy. This is asking for the transition wavelength. Okay, and delta E is equal to hc over lambda. So this equation you have to have as a part of your memory. I mean, it's delta E is equal to h nu as well, but what's nu? It's c over lambda. So
for the 2n plus 1, if you had like a jump from 1 to 3, would you have 2n plus 2?
yeah, if it was 1 to 3, if it was 1 to 3, you'd have to put the delta n equals 2 right here, and you get a little bit different equation. Yeah. We saw there's the general equation in the notes. If you go in, there's the transition equations, and the algebra for the general equation is in the notes, and it's also in chapter 3, I believe, of the book. So if you scan through, you can see the general solution for all delta n's. And I just can't remember that equation off the top of my head, so I went ahead and rederived it for delta n equals 1. Yeah. But if you had that general equation, then you could do it for any delta n and any starting n. So whenever you finish here, notice this is a difference. It's the upper level minus the lower level. So this is your starting n, and this is your final n. So your starting n, and then your starting n plus the change. So n in this equation is always the level you're starting in, if you're going up, if it's absorption. And so if it's a 1 to 2 transition, n equals 1. If it's a 3 to 5 transition, it's n equals 3. So, okay, that took a long time. So if you have a question, we'll jump on to the next.
Could you go over one of the last 2 questions on quiz 3?
Okay. Here we are in quiz 3. These down here, the symmetry setups. Okay, very good. Symmetry setup for the allowed. Okay, so the vibrational, it's the asymmetric stretch in water. So if we go to the notes and we find that, it's this one. Asymmetric stretch means one bond stretches while the other compresses. And the oxygen has to move a little bit to the left to keep it from moving, translating. Okay, so here's my coordinate system. And if you have the notes, can you tell me if this is B2? I can't remember which one it is.
Yes.
Is it B2? Okay, so this is the B2 motion and in C2V character table. Do you understand what I just wrote? That's the B2 row in the C2V character table. So do you have your character tables? You're going to need them. I mean, I'll pass them out for the exam, but like right now you're going to need them. So let's get those out if you have them. I've got a few extras if you need them. Anybody need them? Okay.
So we'll also have the C2 symmetry flow chart. Right?
Yes, you have the symmetry flow chart. So we're looking for the C2V character table, B2 row. And this just says the symmetry setup for the allowed vibrational transition. Well, we would have to kind of do all three to figure out which one is allowed. Okay, so let's go ahead and do that. Let me get my own copy of the character table here. So C2V is right there on the front page, fifth one down. So for the camera, it's this one right here. And so B2, and notice how the arrows are kind of going left and right in the Y direction. So it is the Y row. And in the lecture notes, I show the harmonic potential for this. And vibrational quantum numbers start at V equals 0. The vibrational quantum number is V for vibration. And they go 0, 1, 2, etc. And the ground state is always top row. So we go to the C2V character table, that's A1 for the vibrational ground state. And then this row here is whatever the symmetry of the motion is. And so these are the symmetries of the motion, Y and B2. So it's going to be B2. And then it goes back to top row. Okay? So that's just how the energy levels for vibration are. And we haven't derived that in class, I just told you. Okay? Now, if you were to plot those wave functions, you would see that the 0 and the 2 and the 4, all of those are even by, if you looked at the wave functions, the left and the right look the same. And the 1s and 3s and 5s are odd wave functions. And so it's sort of how they're odd, but in the particle in a 1D box, we only had one option. It was inversion, right? That was the only other symmetry element we had. Whereas in the C2V, we have 4 rows. So we know that V equals 1 is odd, but what kind of odd is it? It's B2. Do you see? So it's odd in a particular way. Every row but the top row is odd in a unique way. And so that's what we're trying to label. We know it's odd, but what kind of is it? Well, it's the symmetry of the motion. If it's, going in the Y direction, then it's B2. If it was somehow doing something in the X direction, it would be B1. So there's different unique ways to be odd. And then there's only one way to be even, and that's top row. Okay. So now that we know what the lower state is, this is for the transition, allowed vibrational transition, let's see, asymmetric stretch in water. I mean, in all of our vibrations, we're going to be starting in the ground state, and so our molecule is right here, and it's in A1, and it's going to be going up to B2. And so we just need to know what polarization of light to use. So what type of light works to cause it to jump from 0 to 1? Okay, so we know that, let's say that the lower state here is A1, and we know that B2 is the upper state. And we know we have to somehow cancel that B2. Because if we look at the direct product tables, which are on the back side, the C2V direct product table down here, we know that any particular odd row times itself is going to be A1. And so we're looking at this and we're saying, I've got to have something that when I multiply it by B2 is going to give me A1. So that when I multiply that by A1, I get A1. And then that will be not equal to 0 and allowed. So does everybody see how we want the problem to go? What do we have to put in at the very beginning? B2. Yeah, if we put a B2, so I'm going to get my different colored pen here, be really fancy. If we put a B2 here, then this all works. B2 times B2 is A1. A1 times A1 is A1. An integral over all space of a top row function is non-zero. And so if I have light that has the symmetry of B2, then this transition is allowed. And so we can look back at our character table, and B2 is Y. So Y polarized light. Right here, Y. Works. Okay, Y polarized light works for that. So, and so this is the symmetry setup, would be this top one here. So that would be the answer, but that's, that's why that's the answer. Yes.
Would you ever ask us for the asymmetric stretch of something that's not shaped like water, like ammonia? In question 10, you asked for the symmetric stretch in ammonia.
Yeah, that's the easier one, right? The symmetric stretch, they're all going down and up in the z direction.
If so, how would the asymmetric stretch work in something
Yeah, it's
not as simple as one?
It's a great question, and we could do it. It's not on the test, so I think we're okay. We'll get into that more as we go forward in the vibration section. So we will answer that question, and I could take like 15 minutes to do it, but I think it would chew up all of our time.
Okay.
Yeah, and so it's pretty simple. It's E. If you look on the C3V character table, so C3V is this third one down here, and the question is, what would the asymmetric stretch be in ammonia? The symmetric stretch is Z, because they're all moving up and down in the Z direction, and the X and Y components all cancel. If we're doing the asymmetric stretch, then by definition, those X and Y components don't cancel. So you're going to have motion in X and Y. Well, look at the C3V character table. This is the short answer. X and Y are on the same row, and it's E. So that asymmetric stretch has to be E without drawing any pictures. Okay, the Z parts cancel because one's stretching while the other two go up, and their arrows are different lengths, but when you add them all together, the Z motions cancel and you have only X motion. So that's just like water. We had the symmetric stretch was in Z and the asymmetric stretch was in one of the coordinates, was in Y. But in C3V, because you have threefold symmetry, X and Y behave with the same magnitude. They have the same energy. They have the same motion. Yeah, so you can't separate them. That's why they're in that doubly degenerate row of E. So it would be E.
Okay.
Yeah. And we haven't done any of the, have we done the, like, E direct products? Have we done any direct products with E? Let me look through the homeworks.
Not really, so.
I don't think so either, because we haven't, we cover that a little bit more in depth later. Okay. Yeah. Yeah, we cover symmetry over and over again throughout the course, and so it just gets a little bit broader each time, and so we'll come back to it where we actually do some more complicated, really complicated direct products. Yes.
How do you know which axis goes where?
Oh, that's a great question. If you have a symmetry axis, like water, so it has a C2 axis right here. You see that? Okay. then there are no other symmetry axes, then that's the z-axis. Okay, so that is z. If you have, let's pick benzene, okay. I'm just going to draw it very carefully, unlike the organic chemists. Okay, it's tilted a little bit. But right here, coming out of the center of that molecule, I'm going to draw a big wedge, right, to show it's coming out. What is that axis? So benzene with six-membered ring and 6 hydrogens coming off, right? What is that axis that's coming out of the benzene molecule?
Is that the z-axis?
No, like what symmetry element? C, well, it could be C3.
C6.
It's a C6 as well. There's a C3, but it's also a C6. So that's a C6 axis. And then I've got a bunch of others. I've got a C2 here. So I've got a bunch of rotation axes, and this is when I need to make a decision for my Z axis. The Z axis is the one with the largest N. Okay, so the largest N is the Z axis. And so if I'm going to draw my coordinate system on here, because I kind of tilted my molecule, look how carefully I'm going to draw my coordinate system. Okay, I'm going to draw it up here like this. And here's the little one coming out at us. Okay, and that is the Z axis. The Z axis, the way I've drawn the molecule, is coming out of the paper. So it's not always just the one pointing up. You align it with the axis that has the highest CN. Okay, and so then it doesn't matter. I mean, so I've got Z here, and I want to do that right-hand rule, X, Y, Z. So Z is my thumb, so X is going off that way. Okay, so this is X here, and this is Y. So that's a properly drawn coordinate system for how I've drawn my benzene, and I kind of tilted it, so that's why my axes are tilted. Okay, and you can just look at this. It does take that sort of counterclockwise motion of X, Y, Z. If you draw your coordinates like that, then they'll always be counterclockwise, but they may just be in different positions. Like up here, see X, Y, Z, still counterclockwise, but X is coming out of the board, and Y and Z are in the plane. Raise your hand if that answered a question for you, like you all had. Okay, good. I'm just kind of seeing what level of confusion there was about the Z-axis. Okay, good. Yes?
I have a kind of more of a question from lab about point groups.
Mm-hmm.
So when we were doing the ethene example in lab,
Yes.
it has the highest order of proper rotation would be a C2,
Mm-hmm.
and then there's 2 perpendicular C2 axes.
Yeah.
How do you determine which of the 3 C2 axes is the main C2 axis?
Yeah, there's some debate over that. Yeah, so I always have to look at it to see if I can figure out. It tells you on this character table, but it's not easy to figure out. So I'm trying to remember. What will happen? No, it doesn't tell you on the character table, but what does happen is if you define, if you and I make different choices, then on the D2H character table, I will say this vibration is B2U, and you'll say it's B3U. And that's why you have to draw the molecule and draw the coordinate system with the molecule. So you're communicating to me which one you've chosen. Okay, so if we draw ethene, can I get you to close that door, please?
Because I know when I done this in lab, I had originally picked one of the C2 axes and then checked it in the I-beam,
Yes.
and they picked a different C2
Yeah,
axis, so I got it wrong.
Yeah, so if I pick this one coming out as the Z-axis, and I kind of like that one because it's like a plate, right? This is how I justify it. So if you're spinning a plate, that has one sort of angular momentum, and if you're flipping a plate end over end, those two angular momentums are the same. So there's one unique angular momentum, and that is the spinning of the plate around its axis. This molecule is nice and flat. It's kind of like a plate. And so the one coming out of the plane of the molecule is the unique one in my mind. Okay, so I would put the Z coming out of the plate. If you got like a benzene, the Z comes out of the plate of benzene. Ethene, nice flat molecule. I think of it the same way, where the Z is coming out. And that's nice because when we talk in organic chemistry about the, listen carefully, unused PZ orbitals, remember that language? The unused PZ orbitals? That's what we're talking about. Those PZ orbitals are coming along the Z axis, which is coming out of the plane of the molecule. And so that's really compatible with the way we think of benzene, having PZ orbitals that are unused in the sigma framework. And then this molecule I treat the same way. So I make the Z axis come out of the plane of the ethylene molecule. But since they're all three C2s, they all could be the principal symmetry axis, and so you could put Z in either one of those directions. So it's just really important for that molecule in particular to tell the person you're communicating with, if you're doing any of this, which axis you chose as Z. I always go with this one, the way I've drawn it.
Okay,
Yeah.
thank you.
Yes. That also makes the plane of the paper the sigma H, because it has a sigma H. Well, it doesn't say sigma H in the character table, so it just says sigma XY, sigma XZ. So they're very specific in saying these are the particular sigmas. So never mind about that. Next question.
I have
Mhm.
one more odd one from
Mhm.
lab, if you would mind.
Sure, no.
Question 9 in lab was the Zwitter ionic glycine.
Yeah.
Where would you determine the center of mass to be of Zwitter ionic glycine?
Yeah. Yeah, so let's glycine, right? So you got the carbon. It's a nice, easy one. It's just got the wedges and the dashes. I'll go ahead and draw this just so you see how I draw it, right? And then you get the carboxylic acid group on one end. Let's do this. It's the Zwitter ion, so this is going to be deprotonated. It's going to be over on the other side. So there's our minus sign. And so this is going to be an NH3 plus. So I'll go ahead and put the H down here in the plane, draw my wedge, and dash. And so that nitrogen's bonded to four things, and so it's a plus. And so if you weren't familiar with what a Zwitter ion is, it's got a plus and a minus inside the molecule. So the molecule is both positive on one end and negative on the other. So that's my version of the Zwitter ionic glycine. You know, the center of mass, who knows? Is it somewhere like this? It's probably not on an atom. You know, it's off someplace. Those oxygens are heavy, so they kind of pull it off to the right and pull it down a little bit. So that's my guess.
Where would you place the Z-axis for this one?
Yeah, so this one, if you go through the flow chart, let's take it through the flow chart. There's no rotational symmetry at all. So we can skip all those questions about C2 axes and everything like that. And we end up way over here. Let's see, where are we? Way down at the bottom. And the only thing it contains is a reflection plane. Right?
Yeah.
So that's the plane of the paper. So let's see, where's my pen? So this is the reflection plane. And so then let's look at the CS character table and see if we can figure out where the Z axis is. So CS, that's this, oh, that's right there. It's up here at the top. So this is the CS character table up here at the top. It's only got two rows. It's got A prime and A double prime. That's a great example of why I say top row, because top row could be A1. It could be A1G if you have an inversion center. And in this case, the top row is A prime. Okay. Now, remember my X and my Y and my Z axes are odd. And so if I change the direction of the axis, that's a -1. So if I have the Z axis here and this is the positive side and I reflect it, now the positive side's over here. So I have to take that times a -1 to get it back, right? So my negative numbers are over here. If I multiply them all by -1, I get the positive side. And if these were positive and they used to be negative, I multiply by -1, now they're negative again. So if I have an axis that comes out of this mirror plane and I operate on it with the mirror plane, that axis is going to flip, right? If whatever axis is coming out of this plane, when I use that mirror plane, that axis is going to flip and be a -1 character. So we need to find the axis under this sigma plane symmetry element that has a -1 character. So we look at the character table and we see that under the sigma H, I have a -1 on the second row and it's the Z axis. So this is telling me the Z axis comes out of that plane, because if I use that plane, the Z axis flips. So that's how I know where the Z axis is in this molecule. So the Z axis is going to come out of the plane and the X and Y axes will be in the plane. And so if I have an x-axis in the plane and I use that, operate on it with that plane, then it hasn't changed. And so there's a +1 for the x. And the same with the y-axis. If it's in the plane and I operate on it with that plane, it hasn't changed. So x and y should be on the top row, and they are. So you can see they're on the top row with a +1 character under the sigma, and the z-axis is in the second row, which has a -1 under that sigma. So that's a great question and a great example of how you use the character table to figure out what the symmetry of something is. You try to look at those character tables. It's really easy to do that when you have the +1s and -1s. When you get to the E's, look at the C3V. You get a 2, a -1, and a 0. What does that mean? So it's not easy to just look at the character table and figure things out when you have an E row or whatever. But if it's one of the single dimension rows, it's pretty easy to figure out once you get your mind on what the symmetry element is doing, like the reflection plane, and how the vibration or the axis or whatever rotation is going to do when you operate on it. Is it going to flip direction or not? So like even rotation, if I had an arrow like this and I reflected it, if I reflected the rotational arrow, it would look like this, and it would be going in the opposite direction. So it would be a -1. If like rotation a lot of times is a -1 under reflection because you change the direction of the arrow. So we've got 2 minutes. Last urgent question. Ooh. There's two. I should have brought an exam. There is one we haven't talked about, but it's the calculus thing. Like you're given like the integral result with the vertical bar, and I want to see you finish that piece. So it's like 2 more steps where you take the expression evaluated at the top and subtract the expression evaluated at the bottom and tell me whether it's going to be 0 or non-zero. We haven't talked about that, and I wanted to give you a warning on that, so just review that again. There's at least 2 handwritten. There might be 3, but it's around 22 questions, multiple choice. So bring the Scantron so I can grade those quickly and then get to the handwritten part. If you're doing a calculation, show me your units, show me your equation so that I can follow your work. If you do get the right answer, but you haven't shown any units and haven't really shown me, the equation or whatever, you'll lose points. I want to see the units. I want to see the equation that you're using in a clean, clear example of why it's the right answer. Yes.
What are you providing us with on the test as far as like
The character tables, a flow chart, a periodic table with some constants and conversions on it. And that's it. Yeah. Yeah. All right. So it's going to be great. Okay. Don't be intimidated. Study hard.